The three greatest unsolved mysteries of the universe. The first question, why do objects fall downward? The second question, why does time slow down near a black hole? The third question, why must GPS take relativity into account to work accurately? If you can't answer these three questions, then please watch this video carefully, because by the time you finish it, you may realize that your entire understanding of the world is wrong. Let's start with the first question, why does an apple fall to the ground? You'll probably say it's because of Earth's gravity, but that answer may be fundamentally wrong, because gravity is one of the most basic phenomena in the universe. It creates a tendency for objects to move toward one another. Apples fall to the ground. The moon orbits the Earth. The Earth orbits the sun. All of this happens because of gravity. It is gravity that prevents these celestial bodies from flying apart. From this perspective, it's easy to think of gravity as a force that pulls objects together based on their mass. The greater an object's mass, the stronger its pull on surrounding objects. Using this gravity is a force model, we can indeed explain why objects fall, and describe how planets orbit the sun. However, the truth is far more complicated. There are clues suggesting that gravity is not a force at all. For example, when we observe a satellite falling toward Earth, if gravity were truly a force, the satellite should plunge straight toward Earth's center. But experiments show that the satellite's trajectory bends slightly, and the direction of that bending exactly matches Earth's rotation. Then there's Mercury's orbit. Mercury revolves around the sun, but its orbit itself slowly rotates over time. The entire elliptical path gradually changes its orientation. If gravity were a classical force, we should be able to predict this orbital precession precisely. But observations show a discrepancy between theory and reality. When we connect these subtle clues, we arrive at a shocking conclusion. Gravity is not a force at all. To truly understand the nature of gravity, we must completely overturn our assumptions about the world, about the universe, about space and time themselves. This is general relativity. The entire framework of general relativity is built almost entirely on a single idea called the equivalence principle. The equivalence principle states that all objects fall in exactly the same way. It tells us that free fall is not the result of a force acting on an object, nor is it an accelerated motion, because free fall is actually the most natural state of motion. When an object falls toward Earth, this is equivalent to the object itself being at rest, while the ground accelerates upward to meet it. Does that completely overturn your intuition? But it's true, even though it contradicts everything we instinctively believe. Falling is the natural state. Standing still on the ground means you are constantly resisting free fall, which means you are continuously experiencing an upward acceleration. This is why you only feel your weight after your feet touch the ground. During free fall, your body follows its most natural motion, and you feel no weight at all, only when your feet touch the ground, and prevent you from continuing to fall. Do you feel what we call gravity? That sensation is actually the ground preventing you from continuing your natural motion. So within the framework of general relativity, gravity is no longer a force. You could even say that gravity doesn't exist at all. It's an illusion. If objects appear to be falling or attracting one another, it's not because some mysterious force is pulling them together, but because they are naturally remaining at rest. The reason it looks different is because the geometry of the universe itself is curved. Objects are not pulling on one another. They are simply moving along straight paths. The problem is that their mass curves the spacetime around them, and it is this curvature that alters the trajectories of other objects nearby. This is the core idea of general relativity. All objects with mass distort the spacetime around them. We can imagine the universe as a vast grid, a structure woven from space and time. When a massive object appears on this grid, it deforms the surrounding spacetime. As a result, the concept of distance changes. The concept of direction changes, and even the rate at which time flows changes. Everything is distorted and reshaped by the presence of that mass. In a natural state, objects always tend to move in straight lines. If we throw an apple into the vacuum of interstellar space, it will travel in a perfectly straight line forever, at a constant speed. But what happens if we throw that apple near a massive object like Earth? Earth's mass curves the surrounding spacetime. The straight lines themselves become bent, all converging toward Earth. So when we let go of the apple is still moving in a straight line, but that straight line has been bent by Earth's mass. As a result, the apple gradually moves closer to the ground. This effect is what we call gravity. When an object has enormous mass, it can distort the structure of spacetime itself, causing all nearby straight lines to curve toward it. Everything around it moves along these curved straight paths, ending up closer and closer to the massive object. To better understand this, let's imagine two scenarios. In the first scenario, two people stand on a perfectly flat plane and walk forward along straight lines. Because the surface is flat, their paths remain parallel, and they never meet. In the second scenario, the same two people stand on the surface of the Earth, and walk straight north. The Earth is a sphere, a curved surface. What happens? Even though both people walk in perfectly straight lines, something strange occurs. When they reach the North Pole, they meet. Each person walked straight ahead, but because the surface is curved, the straight lines themselves are curved. As a result, it feels as if some mysterious force is pulling them closer together. Through this example, we can better understand how gravity emerges from curved spacetime. Objects appear to attract one another. Their paths seem to converge, but in reality, this happens simply because straight lines are distorted in curved spacetime. To demonstrate the strange phenomena predicted by general relativity, let's look at one of the most mysterious objects in the universe: black holes. A black hole is an object with an enormous amount of mass, but nearly all of that mass is concentrated at a single point. We call this point the gravitational singularity. At this precise location in the universe, the structure of spacetime is infinitely distorted, and modern science still cannot fully understand what happens there. Near the singularity, spacetime is curved so severely that all straight lines point in the same direction, toward the singularity itself. Here, nothing can escape a black hole's grasp, not even light, because every possible path leads into that ultimate abyss. Black holes emit no light, matter and radiation cannot escape them, so what we see is a perfectly black sphere. Surrounding it is a boundary, known as the event horizon. Once you cross this line, there is no return. Outside the event horizon, a black hole behaves much like any other massive object, but as you approach the horizon, maintaining a stable orbit becomes impossible. Spacetime is too violently distorted, motion becomes chaotic and unpredictable. However, if you remain far enough from the horizon, you can orbit the black hole stably. Interestingly, light from distant galaxies bends as it passes near a black hole. We can observe distorted images of stars that lie behind it. This phenomenon is called gravitational lensing. There is an even stranger effect. When a black hole rotates, if it spins fast enough, it drags the surrounding spacetime along with it. An object falling straight toward the black hole will be deflected by this rotation, its trajectory bending in the direction of the spin. This bizarre effect also applies to Earth. Earth's rotation slightly deflects the paths of falling objects. Now let's look at the most puzzling phenomenon of all: gravitational time dilation. When you approach a massive object, not only are your straight paths in space distorted, but the time dimension is distorted as well. As a result, the flow of time changes depending on your distance from the massive object. Far from a black hole, space-time curvature is barely noticeable, and time flows much like it does elsewhere in the universe. But as you move closer to the black hole, you'll find that your clock runs slower and slower. Near a black hole, space-time is so severely warped that when 1 second passes for you, an entire year may pass for a distant observer. In general, the closer you are to a gravitational source, the slower your time flows. For example, if we compare two clocks, one at the base of the Eiffel Tower, and one at the top, we find that the clock at the base runs slightly slower, because it is closer to Earth's center. How much slower? About 1 microsecond per year. This effect is tiny, but critically important. When designing GPS satellites, this time dilation must be precisely accounted for, to keep satellite clocks synchronized with clocks on Earth. Otherwise, your navigation system would produce serious errors. In summary, general relativity provides a complete framework for understanding gravitational phenomena. When massive objects exist in spacetime, they distort the surrounding geometry, causing straight lines in both space and time to curve. This alters the motion of nearby objects and changes how they experience time. Beyond explaining gravity, general relativity leads to many other astonishing predictions. This is general relativity, a theory that tells us gravity is not a force, and that falling is actually the state of rest. A wildly counterintuitive theory that completely reshaped our understanding of the universe. And its most remarkable feature is this: for more than 100 years, it has passed every experimental test.